Okay, so this is the final chapter, is chapter 10, and actually I wanted to concentrate on a design issue in relation to obviously distributed systems. This is what I've been trying to tell you all for people who went through the 530, remember computer architecture. I always made emphasis on distributed architecture because by the end of the day 530 is just a prerequisite for the 611 network operating systems. It is actually a prerequisite for so many other courses. Anyways, so Google case will be our study for this chapter, and we start with the following question. Now this is just again an introduction, and as usual question number 1 will be very beneficial to the other questions. It just lays the foundation for this chapter. It gives you some keywords in relation to Google, well, specifically on cloud technology actually. So to what extent is Google now a cloud provider company? I mean, most of us do have some sort of interaction with the cloud, and it is as follows. Now, to define cloud, this is what we defined last time we met in the 530. Again, a set of internet-based application or applications. Okay, storage and computing services. Now those all will be under some sort of a give and take, i.e. a client-server communication. Both play a role as far as uploading and downloading information. So those services, those in relation to the server client, those should be sufficient to support most users as far as their own applications or needs or whatever is required for that transaction. This will mean that those clients will be enabled so that they are somehow, they are largely or totally circumvented from their local storages as far as their applications, because most of the applications will be, or actually will reside, in the cloud. Okay, now back to Google. As far as Google concerned, this cloud in relation to Google services, those will offer the following four, let us say, services slash aids. The first one is a so-called Google File System, the GFS. Now this is a large file system, a distributed file system for large distributed data intensive applications. Now when I say, or when you hear people, when you hear a so-called data intensive applications, this relates to the scale and it relates to real-time processing. Scale and real-time processing. This is number one. Second, choppy. Now this is a security type of service, is a lock for security, service for loosely coupled distributed systems. Now note, the phrase loosely coupled, not tightly coupled. Obviously it is loosely coupled because you are talking about the cloud. Number 3, big table. Now, big table, think of your databases, or at least the fundamentals of database. So this is a distributed storage system for managing, as in database or databases, managing structured data that is designed to scale to a very large sizes. Now, when it says a very large sizes, think of replication and updating. You see all these points that I'm adding to what you already have on your screen, you'll see in the subsequent questions. And lastly, the reduction or map reduce. Now, map reduce, this is something used for data processing, obviously. It is part of the Google service, and it is mainly, or it should mainly deal with real-time processing. Although it has been changed to a so-called cloud data flow. So back to MapReduce is a programming model and an associated implementation for processing. Remember, real-time processing, for processing and generating large data sets. Okay, now in time this was replaced. Actually, it was replaced, fully replaced in about 4 or 5 years ago. This was replaced by a cloud data flow. Now, the difference between the two is as follows. Looking at the definition, or a related definition to cloud data flow. Now, this is, or the cloud data flow is a cloud-based data processing service for both, notice, for both batch and real-time data streaming applications. Now, with the MapReduce, it has some problem. It did have some problem with real-time data streaming, so it was changed fundamentally and gave birth to a so-called cloud data flow. Now, although the cloud is present, the problem with the cloud, and this is current, is security. We still have some issues with security as far as the cloud. I'm not saying that it is the problem or the main problem. There are other problems, but security is still an issue with cloud. So Google can now be viewed as an extensive provider of cloud services, and everybody agree. I don't think anybody can disagree with this. Those services offering both software and kernels or platform as services. It can provide both software and platforms, as in kernels, but not yet operating in the domain of infrastructure as a service. And this is all to do with the communication channels. This has nothing to do with security. This has to do with communication channels. Now, probably in the next, I guess in the next 5 years or 8 years, some of the issues relating to the infrastructure or such infrastructure should be alleviated. Security, I think it will take a little bit longer. So this is just a taste of what cloud technology versus Google. Question number 1. Do we have a question on one, people? Do we have a question on 1? Do we have a question on 1, people? Wake up. Come on. Can you hear me all? Somebody says yes. Does that mean that you have a question, or yes, you can hear me? Okay. Right. Right. I'll move to number 2. We'll move to specifics as far as services, the GFS, Google file system. Okay, it says the following. Number 2. The key requirements for the Google infrastructure are, obviously this is a cloud-based technology, so scalability, number 1. Reliability, number 2. Performance, number 3. And the last one, well, this is just an addition for completeness. It is not 100% being implemented. Openness. So the question says, provide 3 examples of where these requirements might be in conflict, specifically when it comes to scalability and reliability. As we will see, they both will affect performance. And then discuss how Google deals with these potential conflicts. Okay, now in relation to reliability, performance, there is a conflict between those two. So you need to have policies as introducing measures to increase reliability will inevitably carry an overhead, i.e. performance. So those two somehow conflict. Same goes for scalability, obviously. Now, in relation to this point, a good example is replication. So replication is often used to increase reliability. Obviously, with more replications or more replicas, clients will have ample of time to receive and process whatever is required, because there is a replica somewhere nearby. Okay, it is used extensively in Google. And now this does not require additional algorithms to maintain consistency of replicas. This is just a copy. Now, in order for reliability to be present, so the key is to implement reliability in such a way or in a manner to minimize the impact on performance. Now, performance in this case is defined as follows. Compared to the bandwidth available, how much data being sent to the receiving end without repetition. Performance, how much data being sent to the recipient without repetition. Because if you have repetition, it means that your channel suffers from, let us say, attenuation, noise, distortion, whatever. So think of performance as how much data is being sent from A to B, B being the recipient. Again, the key is to implement reliability in a manner that minimizes the impact on performance. And an example is being given. Okay. So for example, to have relaxed consistency between replicas, between what is available on, let us say, a number of servers in your net or your internet. And this strategy can be seen in GFS, the Google File Systems. For example, there are implemented policies in order to cater for those replicas. Now remember, those replicas must be refreshed. Again, those replicas must be refreshed. They must be updated. So think about replicas and real-time processing being maintained by those replicas so that they should always be consistent. And the only way you can be consistent is to have a newly fresh copy. Okay, now back to the GFS. GFS also support big table and MapReduce. Lately, it is actually the data flow part is being serviced too. So GFS supports the big data and MapReduce. Actually, those two can have significant impact on performance for a simple reason. We are talking about large amount of data, and when you do have a large amount of data, think of how consistent and correct the data must be received by those nodes or recipients. So performance issues will be affected specifically with large data type. Now, in as far as big data, the big data or big tables, those allow control to be implemented in an original or a master original copy. Now this is held in a server, so you have to bear in mind that you must have a master server. So those masters are servers responsible for metadata. Now metadata is the in-between process. Metadata is the in-between process. It is a set of data that describes and gives information about other data. So it is the in-between, it's a transit type of information to relate to other information. It is the same like an index. An index will refer to a location. It does not give you the content of that location. So as far as those metadata, those are just indices for data processing, and they relate to other data. Also, there is a potential conflict between reliability and scalability. Now this should be obviously seen when you consider large scale networking system. Now the larger the network is, replicas will be much more harder to maintain or to update or to refresh. So reliability is inversely proportional to scalability. High reliability, small scale. Low reliability means that you're talking about larger scale networking system. So collectively with this strategy, it can help with scalability. This is done by reducing the overhead. Now, how to do that? Again, with divide and conquer I mean, this is the only thing that can be done, is to segment the whole network, this large network, into zones for which you have masters, a number of master servers. Okay, this will provide some sort of consistency, i.e. consistency management. Now, Google makes use of this extensively in its own physical infrastructure to ensure that services can scale, i.e. to divide and conquer. And lastly, there is also a potential conflict between openness and performance. Now, openness, this is in relation to acquiring more than one consistent type of communication protocol, i.e. the ability to maintain communication with other structures or infrastructures. It is just like when you go, say, let us say you go to France and you cannot speak the French language, so you need an interpreter. If you go to Sweden, you cannot speak the Swedish language. But if you do, we will say that this system is open. It can cope with other infrastructures. So the potential conflict between openness and performance, this is in relation to this converting or this conversion. Of course, you need some sort of a converting protocol from one infrastructure to another. So the temptation in supporting openness is to provide generic. Now, the word generic is very vague, but it means that we will create a language that is understood by everybody. Now, English is somehow understood by so many countries. It is not in others. So we cannot say that if you speak English, you can make a way for whatever you want to do in, let us say, in France, because most of French people, they don't like to speak English, and so on. But back to Google, it is trying to provide a generic platform so that it can cope with other infrastructures. This is why when I started the question, I relate to the word openness as being a little bit vague. Okay, people. Question number 2. Do we have a question on 2? Do we have a question on 2, people? Talk to me. Okay. Here we come to the protocols. Remember, I was talking about the infrastructures and different protocols. This is what I mean. Question number 3. It says, discuss the extent to which the RPC, remote procedure call, this style is or to be supported by protocol buffers. Now, protocol buffers, those are just arrays, registers, a number of registers, a memory map that can be dynamically allocated. Again, can be dynamically allocated. So if we were to be provided with those buffers, how does those enhances extensibility, scalability, extensibility, and future growth? Specifically, the design decision to have one argument and one result. We are back at the generic standard. This is what this question is trying to emphasize or put emphasis on. Okay, let us start with RPC. So those are protocols. Okay, is a protocol that one program can use to request a service from a program located in another computer. That's why it is called remote. Okay, without having to understand the network's details. So it is somehow a standard generic way to communicate remotely. RPCs. This is one way. Then you have to have the hardware / software, obviously, but mainly hardware to get along with this type of a procedure, i.e. the remote procedure call. Interfaces. So interfaces, those they are defined in terms of operations, the actual hardware actually, how it ticks along the way to provide or to lay ground for that software, which is the RPC. This take data in and produce data out, and more likely to be stable than more general interfaces. Now, because they are generic, obviously they should be more stable. They should not have any delays. They should not have any problem as far as data rejection. And those are defined in terms of a so-called RMI, the remote method of invocation. Remote method of invocation. Now, RMI is just a way, it is some sort of a tweak, an interrupt, and a control type of a procedure that a programmer may use, probably Java programming language. This is actually used to write an object-oriented programming scheme in which those objects on different computers can interact. Now, this interaction obviously will need some sort of a generic converter, and this is what I've been trying to say in question number 2. This is how you may interact with other disciplines remotely in your distributed network environment. As an example, so for example, which will have arbitrary parameters including object references. This is just a question. If you were faced with such a problem, this shares similarities with the so-called reset philosophy, where the complexity is pushed towards the data and interfaces in this case are simple to be built, i.e. it is just a buffer that will accept, let us say, a black box. Now, in this black box, you will have your data. But you see, this black box itself can go back and forth between those two interfaces using those RPCs based on whatever a programmer has inserted according to a specific RMI. So RMI will work with the RPCs in those black boxes to provide whatever data. Now think of data inside the black box containing different type of information, and actually the formation and the structure of this data in this case will no longer be an issue because it will be contained in a generic box, what I am calling a black box. Now, those reset and complexity procedures, this is just like the push and pop instructions in the stack. You have a push statement or a reset and a complexity statement, which is to pop. So you are pushing and popping through that link data, but using that black box. So those two features, or both features, are potentially supportive of more extensible interfaces, i.e. they can scale up with so many interfaces. And this is the heart of the question, is to provide a way in which you may mingle or you may send data with different structures to different interfaces using specifics based on RPCs, RMIs, and those little or large black boxes, depending on how much data is to be sent from one side to another. Question number 3. Do we have a question on those protocols, RPCs? Question number 3. Do we have a question on the 3 people? You sound very tired, or something is wrong with the link. I don't know which one. Okay. Again, with chubby GFS and big data. Number 4 says the following. It is also based on the cloud structure, Google infrastructure. So it's explain why the Google infrastructure supports 3 separate data storage. Now, since we are talking about large data to be stored, so the cloud is in concern here. And when it comes to cloud, think of your security. Okay, why does Google not just adopt a commercial distributed database instead of utilizing the 3 separate servers? So you have 3 separate services, okay, in your Google. So the question, why is there dedicated Google services but not to rely on a commercial distributed database? And here it is. Now, Google are very proud of their produce or products. They are actually they want to maintain a so-called high performance versus scalability. So they really designed their system in such a way to interact with many or multiple disciplines. That's why they have their own. They cannot rely on commercial distributed database because those are somehow alien or generic to Google. Okay, so in terms of Google viewpoint, this is to provide minimal service that do not really have low efficiency, or they do one task efficiently. They don't have any issues in between, so they will do their tasks efficiently. Somehow, some of the services, when they start to cross, you will have a so-called overloading, and even with the best performance channels and the best performance load balancing, you cannot get away with delays. So this is their viewpoint, at least Google's viewpoint. So Google therefore provide 3 minimal services. Those have distinct jobs. Okay, one is different than the other. And they are, as I said earlier, those are the GFS, as defined here and above, Chubby, and Bigtable, as defined above. Now, although they have provided those 3 services, Google would not want to use a commercial distributed database for 3 main reasons. Now, they have their own, and they have a case against commercial distributed databases. In comparison between the GFS, Chubby, and Bigtable, performance / scalability, I think you'll appreciate why Google have a tendency to use their own services. So they prefer to own and be responsible for their entire code base. Obviously, this is called compatibility. They want to cater for their own compatibility, and point taken. The second one is a little bit, it might be not clear. Distributed databases are not tailored towards their own operating environment. Now, this is true until 2012. People started to use a sort of standard platform, so Google have not really have a big point when it comes to comparing their operating environment with others. They are so similar. Okay. One example is for dealing with massive data sets. The majority of other commercial distributed databases are using somehow the same data sets, or at least they look at those data sets in a similar way. So point 2 is a little bit shaky, but then again, this is Google. The third point is valid. A distributed data set, for example, relational data sets, and I given a definition. Now, those offer rich functionality which goes beyond what is necessary for Google. So maybe if you look at point 3, you might return to point 2 and say, okay, now Google may have a point. But then again, it is only for this point that extra workload is being implanted in those commercial distributed data sets that will be not so beneficial to Google. Because, I mean, if you go back to the Chubby and the Bigtable, some of the manipulations or data manipulation is done there is sufficient. So this is why actually Google do not use commercial distributed databases, and specifically is point 3, and somehow point 3 reflects on point 2. But to my knowledge, point 2 is no longer is the case, and as I said, starting from 2012, 2013, so many vendors started as far as commercial distributed databases. They are moving towards providing some sort of a generic type of distributed databases, so everybody can work with them quite effectively. Okay, question number 4. People, do we have a question on 4? Okay. Sonny, Lee, Kula, are you there? Tushar, Patel, Sweetie, thank you, sir. Okay. Right, now moving to 5, number 5, it says both GFS and Bigtable, remember those two services, make the same core design choice. Now this is based on the following, is to have a single master. We dealt with this above. Okay, now the question is, what are the consequences of failure of this single master in each case? Now, before I go to this question, I mean, everybody should think in line of single point failure, i.e., if you somehow have a node and this node concentrates all inputs to be processed and outputted to the other side, if this node or this single nodes goes down, the whole process goes down. So single point failure is a big problem. Okay, so back to the question. A master server. Now think of a master server and think of duplicates and think of updating. Masters, duplicates, updating. Right. So a master is responsible for metadata. Okay. Back to its definition. This is a set of data that describes and gives information about other data, a transit type of a scheme to other data. Now for the master server, this decision to have a master server, to have a single master, was made particularly in GFS. Reason: to simplify the design process and allow Google to get a production system and operation quickly. Actually, this is not good enough reason, but that was the reason given at that time. Okay, so point taken. This is a first impression design and they stuck with that first impression. Now they are trying to make a case for this point or single point of failure. So although this is a single point of failure, if something goes wrong, the whole system goes down. Failures can be detected and the master restored. So how is this done? This is supported by the fact that key metadata is stored in a persistent operations. Now persistent operations means there is a refresh. Again, there is a refresh procedure or a process on those replicas, i.e. replicas are being updated and stored. Replicas are being updated and stored. Okay, so the key metadata is stored in a persistent operations log and this is replicated on several machines, enable relatively rapid recovery. So what this is telling us, just imagine an octopus. Again, just imagine an octopus. An octopus has got a center, his or her or its brain, and then you have a number of legs. Now, by at the end of the leg, each leg, you have some sort of a storage system. So you have a centralization, which is your master. Linked to that master, a number of servers providing service. Now, those servers are dedicated to provide replicas. Obviously, you don't have only one. You must have different storage devices. This is why I'm giving you an example. It is exactly like this. The model, I've seen the model. It is exactly like this. Just like an octopus, a central brain, and then you have different legs. By the end of those legs, you have different storage environments or storage areas, and those storage areas are updated automatically and persistently, and they do provide a backup. So this single point of failure is dealt with backups. Okay. So other data can be restored by polling the chunk service. Remember the end of each leg of the octopus, chunk servers. Okay, those are data splitting servers. Those are the servers that will feed information back to the brain or to the central point once it is needed. Not all the time. It is going to feed information if it is needed. There will be a short delay from failure occurring to being detected through the master. Obviously, it will take time, at least for the duration of the propagation, a so-called propagation delay from the end of each leg to the brain, just to provide the correct replica, the correct sample, a so-called chunk service. Okay, so this is restored, and this will disable operations that requires the master, but not ongoing transfers as they bypass the master. i.e., is going to feed information to the master. It will stop any information from the master. This is what is actually saying. So think about this example which I have given you, an octopus with, let us say, 10 or 20, for example, 10 and 20 legs. End of leg, you have a so-called server or chunk server. Once there you have a problem with the central point or the head, chunks of data are being fed. So you have to somehow stop, or you have to have some sort of a stop band from the head to the chunk service, but not the reverse, specifically when you want to update. And that's it. It's as simple as that. Question number 5. Do we have a question on 5, people? Come on, talk to me. Do we have a question on 5? I bet that you are sad because this is the last chapter. That's why I don't see any response from you. Don't be sad. We will meet again probably after your exam. So you should be okay. So be happy. Oh, Sachin said no, he's not sad. Okay. So you are happy, my friend, because this is the last lecture. Sachin. Okay, that was a joke. Thank you. Right. Question number 6. With 6, we're going to specifically concentrate on the chubby or on chubby service and how replication is done there. So it says when comparing the cache consistency, remember cache consistency and cache coherence problem that we dealt with in the architecture, the 530, if you remember. So when comparing the cache consistency approach in Chubby with NFS, the NFS offer a much weaker semantic control for those data actually. So NFS offer much weaker semantics in terms of seeing different versions of files on different nodes, i.e. when it comes to the comparison part. The question is, perform a similar comparison between cache consistency approaches adopted in Chubby and AFS. So it is NFS, AFS, and Chubby. Now, NFS is network file system. It's just like a directory. Okay. With AFS, this is the Andro file system. It is a derivative of NFS. We'll come to that. Okay. So in Chubby, this will specifically explain the consistency management part. So in Chubby, clients cache data, and when a mutation or change of the structure occurs, this is a flag, obviously. This operation is blocked by that flag until all other cache entries are invalidated, i.e. to start a new fresh memory map. So caches are also not updated directly, but rather updated, or updates go through the server. So you have some sort of an interrupt for the cache. Now people think of many processors or multiprocessors having multi cache systems, and those cache systems must be updated. You must have some sort of consistency between those caches relative to those processors, at least for that session. So time is of an essence, i.e. those replicas must be consistent at least for the duration of that operation or session. Okay. If this is done, this ensures deterministic results, i.e. whatever you have as far as information, you can be sure that it is the correct one. So this ensures deterministic results, i.e. given a particular input, it will always produce the same output. And this is true for cache, because if you're talking about if you are talking about, let us say, 10 caches or 10 different caches, you want to have the same input being outputted on those different caches. You want to have replicas. This is why we are interested in a so-called deterministic results. You want to be assured, you want to be determined that what you have is the same for all other caches. This is why it's called deterministic results. Okay, now in AFS, the Andro file system, this is the AFS. This is a distributed file system. It uses a set of trusted servers. This is just a policies or a number of guarantees, policies or guarantees, a set of trusted servers to present a homogeneous, location transparent file namespace to all the client workstations, i.e. the same replica. This is replication. This is part of the replication process. So when a server receives a request to update a file, one server, a callback is sent to every node just to make sure that if there is going to be an update, everybody should get that update by this call. With a cached copy, i.e., remember the deterministic approach, with a cached copy, and this will cancel this copy, i.e., updating it. When you cancel the current one, it means that you're going to update it with a newly fresh one. Now, those two schemes, Chubby and AFS, those are very similar. You know, when you're talking about the deterministic result in Chubby, it is somehow being done in the AFS. It might follow some sort of a different mechanism, but the end produce or the end result is the same. Consistency. Okay, so Chubby and AFS are very similar, and both offer more deterministic guarantees or deterministic results. As compared to NFS. Now, NFS, by definition, this is a client-server application which lets a computer user view and, this is a big point, optionally store and update files, optionally, okay, on a remote computer, as though they were on the that user own computer. Now, the key difference between those, so the key difference is that in AFS, a callback message may be lost, and this can result in clients accessing not an updated version. Obviously, they will access an old copy of that file. This does not mean that the AFS is not used or there is a fault in AFS. Actually, NFS as compared to AFS, in some schemes, AFS is far more superior. In some channels, AFS might lag behind, but then again, AFS is current, it has been used, it is used heavily, especially in short bursts of data. With short bursts, you don't expect a high probability of errors. That's why AFS is used more than NFS. Okay. Number 6. Do we have a question on 6, people? Question number 6. Do we have a question on 6? Well, Rue said no. Okay. Number 7. Now, this is a different ball game actually. This is very similar to the TCP, Transmission Control Protocol. If you remember the transport layer in your network, old network stuff, this is very similar to TCP. Okay, it says the implementation of PACs depends on the generation of increasing and globally unique sequence numbers. Describe an alternative approach to implementing such sequence number. Now, what is a sequence number? Let us say supposedly I'll choose one of the students here. Ru, are you there? Ru? Anybody? Ru, are you there? Kola, Lee, who's there? Tushar, Sweetie. I'm trying to see who is there. Okay, Tushar is there. Now, Tushar, bear with me. I'm just trying to explain sequence number or sequence numbers. Let us suppose that I'm going to send Tushar 10 messages. message number 1, 2, 3, 4 up to 10. Now there are two ways in doing that. I can send message number 1 and ask Tushar to send me an acknowledgement receiving number 1. When I do get it, I will send number 2. If I don't get it, I will repeat on sending 1 until I get an acknowledgement for 1. I go to the 2, message 2. Same goes for 2. I must make sure that 2 has been received by an acknowledgement from Tushar, and so on. This is one scenario. The second scenario, I might dump all the messages, send 1, 2, 3, 4 up to 10 to Tushar, and then wait for Tushar to send me a message telling me that he has not received message 2, 6, 8, and 10. Then I will send 2, 6, 8, and 10 separately, or repeat sending those. Are you with me, people? Two mechanisms. Either being persistent on sending each, or dumping the whole messages and then waiting for the recipient to send me a message telling me whether he received the whole bunch or not. If not, B, i.e. the recipient will send those messages which was not received. Back to the question. Thank you, Tushar, if you are there. Okay, you are there. Good. I'm just teasing the others because I cannot see others saying anything. So thank you, Tushar. Okay, back to 7. It says the implementation of PAX depends on the generation of increasing and globally unique sequence numbering, which I have just explained. Describe an alternative approach implementing such sequence numbers. Okay, so such algorithm or PAX algorithm is for some number of peers to reach agreement on a value. So this is a starting point. Let us say the starting point is 0 or 10 or whatever. Reach an agreement, and there is a reason for that agreement. And this will be used as a reference point. So this algorithm or PAX generates this number, and PAX guarantees that if one peer believes some value has been agreed upon by the majority will never agree on a different value. And this is it. Everybody agrees with a number. To tell you the truth, 20 to 30 years ago, or maybe more, 40 years ago, people used to do the same, specifically with security or data security. They used to provide a so-called timestamps, and this is the same. It is actually the same. The only difference is with timestamps, they are ever changing in accordance to current time and future times, while this algorithm is generated randomly with a reference point. Okay, so what is required is that the sequence numbers are unique, and unique as in to be chosen and agreed upon by the majority. This is the uniqueness of that number, nothing fancy. Unique because majority agreed on that number. But the second point is important. And monotonically increasing, i.e. always increasing in the same order. Now this is important, i.e. when you start with 0, you don't go back to 0 or -2. When you start with 10, okay, you don't go back and say, okay, now I'll start with 2. You can't, because as I said, this is a reference point, and from that reference you go up. Okay, and there is a reason for that. It is by the end of the day, the receiver will start counting whatever it received as messages. And this is usually done by administrators by the end of the day or the end of the month, just to weigh out the performance of the system. So he or she or the administrator must always have a reference point that does not conflict. Now imagine in this case, if you start with 10 and then you go back and start with 2, the whole scheme will collapse. This is why you have a unique sequence number agreed by the majority. Very easy. The second one, it is monotonically increasing, and I gave you why it should be monotonically increasing. The last paragraph says another way of achieving this is to form a sequence number from a combination of timestamps. Remember timestamps? An easy way to understand timestamps. Our timestamps for this session is at 8 o'clock sharp. This is a timestamp. Now it is 7 minutes past 9. We might consider this as a timestamp. Now 9:07 a.m. p.m. excuse me, okay, as compared to 8 p.m. is 1 hour 07 minutes. So a timestamp is just like saying we are going to go back to the old days, 40, 50 years ago, which is actually, most of us, I know I use them. I use timestamps specifically to achieve some sort of performance gauge to my codes or student codes when they start programming different segments of their projects. Okay. Question number 7. Do we have a question on 7, people? Do we have a question on 7, people? Talk to me. Come on, guys. Okay, thank you. Okay, last question. Okay, so bear with me. This is the last question. It says the following. This is an easy one. So this is a very easy question. It says provide an example of a distributed computation, and here it is, that would be difficult to implement in MapReduce. Actually, I made this case above. This is just a repetition, but I just wanted to clarify things with a question, giving full reason for your answer. So what is this saying? Why Google got rid of MapReduce and then turned to cloud or data flow or cloud data flow? And this is it. Here it is. So MapReduce, this is by definition a programming model associated with implementation for processing and generating large data sets. Okay, we know that from previous knowledge. This is designed to work well with applications that fit, and here it is, the pattern of taking large data sets, performing the same operation, the map operation. It's just like a memory map. It goes on and on. Okay, that's why it's called MapReduce. On different chunks of this data, the output of which or producing a set of intermediary results. And here is the reduction. The reduction is being maintained here. References or intermediary results. Sorting these intermediary indices or results by intermediary keys or indexes or indices. Then combining these intermediate results into a single value or values. And here is how they reduce the data set. And that's why it's called MapReduce. So what is wrong with MapReduce? The line in the middle. This is a flexible model that matches many styles of distributed computation, but not all. So it is not generic. So Google thought of moving to a different scheme. Okay, in order to give you some sort of analogy or try to convince you, the last paragraph should be clear. Consider, for example, a computation, some sort of manipulation algorithm, heavy algorithm, that follows a pipeline pattern. A pipeline, remember pipelining, the concurrency in pipelining, where the results of one computation fed directly into another, and so on. A pipeline, that's why it's called a pipeline. Okay, now we are talking about MapReduce, and we have an application relying on this pipeline pattern. This is fundamentally a different programming pattern that would not repeat, would not work well in MapReduce. There are many other examples of distributed computation that do not fall into the pattern supported by MapReduce. Now, the reason why it does not work, because you see, if you go back to MapReduce, MapReduce produces indices or keys of individual data set. It does not have a link between those data sets. But here, with a pipeline, those data sets are fed from one to another, pipeline people. So obviously MapReduce will fail. Note that MapReduce is replaced by a more lavish type of algorithm, which is cloud data flow. And as the name given, data flow, actually data flow is a process that is used in parallel processing, and it relies on pipelining. So that's why the reason I relied on this pipelining, just to make sure that MapReduce will not work, and then give reference to cloud data flow because it relies heavily on a pipeline parallel processing type scheme for the reduction or for data reduction. And that's it. Question number 9. Do we have a question on 9, people? Please, if you have a question, say so. For heaven's sake, if you have a question, say so. Anybody? Do I have to call you by names? Come on. Okay. Now, if you have a question, thank you, Lee, thank you, Ru. If you have a question, people, stay on. If you don't have a question, thank you for attending. I will see you probably, hopefully, when you have your exam is on the 11th. I will see you next week. Okay, I will see you next week. We'll have a chat. I might find something to talk about with you. This session, which will be given to you next week, will have nothing to do with your examination. You will be going to go through the examination with chapter 6, 7, 8, 9, and 10. Next week lecture actually will be on something that is extra, which is not included in your examination. I will choose something that is relevant to your topic, which is network operating systems, and then we have a chat about it. Okay, thank you people for attending. I'm not leaving until the last person leaves. Again, I'm not leaving until the last person leaves. Pital, are you there? I've never heard from Pital. Okay, thank you, Ru. Pital, you're not there. You're never there. Your name is there, but you never talk to me. Okay, Tushar was there. Tushar 2, actually. This is Tushar 1. Kula is not there. Is that Anurag? Anurag is not there. Pital is not there. And Kula is not there. Okay, people, I would like to thank you all for attending. I will see you next week. As I said, we will do something in relation to 6.11 network operating system. or systems. I will see you then. Take care. Thank you for attending again. Bye bye.